Hi everyone, welcome to the ME296 lecture on voltage, current, and resistance. In this lecture we will cover energy, potential, and voltage as they relate to circuits, how electrons become current, and the foundations and physical properties of current, as well as how electrons resist becoming current, as well as the physical properties of the material they are traveling through. First up is voltage. Fundamentally, voltage is energy, which has units of joules or kilograms meters squared per seconds squared. While energy can be a lot of things, we are interested mostly in the energy that allows objects to perform work. Circuits also obey a form of the law of conservation of energy, or that the total energy of an isolated system remains constant. We'll develop this a little more as the course continues. Now, there are several types of energy, each of which behaves virtually identically to the others. So before we get into the more abstract voltage world of potential energy, let's start with something a little more familiar, gravitational potential energy. So if energy is equal at all points, if our ball is sitting on a flat field, nothing interesting happens without outside help. The ball will just sit there. But when energy is not equal at all points, like on the hill, we have a higher gravitational potential energy at the high points of the hill and a lower gravitational potential energy at the low points. And if you place a ball on a hill, it will spontaneously roll from the top to the bottom, or from areas of high potential energy to low potential energy. Now, this is called a spontaneous event, and it happens due to the unequal distribution of gravitational energy, or potential, which is the difference in these two energies. So this form of potential energy has the hopefully familiar equation, U equals mgh. There are other types, including spring potential energy, shown as the second equation there, as well as electromagnetic potential energy, which is the type of energy we're concerned about with circuits. But before we go to that, one slight modification. What if we install a catch halfway down the hill such that the ball cannot continue beyond that? Any energy beyond that catch is not available to the ball, so it can't convert that potential energy into kinetic energy. So in practical terms, we don't need to include it in our calculations. We can just define the gravitational potential energy at the catch as 0. Everything after that would become negative, but we don't have to worry about that because we're not including it in our calculations. Our system does not include this negative energy. So there's nothing wrong with defining arbitrary points as 0 as long as we don't have to deal with it in our system in such a way that would create a non-physical reality. So now on to circuits. In an active circuit, voltage is the electromagnetic potential internal to the circuit. And this potential can be provided by a battery or a wall outlet, magnet, some other stuff. And because this is an electromagnetic potential, it causes particles that have a charge, either electric or magnetic, to move from areas of high potential to low potential in exactly the same way that gravitational energy causes objects that have mass to move from areas of high gravitational potential to low gravitational potential energy. In particular, the things that move inside of our wires, inside of our circuits, are free electrons, which are electrons that are not bound very tightly to an atom's nucleus. So in classical mechanics, if we roll 100 identical balls down the same hill, we wind up with identical results. However, the situation is not quite so simple for electrons. At that scale, even before the electromagnetic field is applied, electrons have some energy on their own, and this can come from things such as temperature or kinetic energy. The important part is that this additional energy can affect the electron's velocity as it moves towards the low potential. And we know from our physics classes that this internal energy follows a Boltzmann or normal distribution, which we can reduce to mean that there is an average energy for the entire population of electrons. On average, each electron will behave as if it is affected by only the average energy. To reflect this into voltage, we normalize the energy of our system by the number of electrons, where we count electrons in coulombs. And a coulomb is an integer count of electrons of 6.24 times 10 to the 18th electrons. So what this really means is that when we say a volt of energy in our circuit, we mean that we have 1 joule distributed over 1 coulomb worth of electrons. okay? And then just like in the previous example where we installed a catch halfway down the hill, we can define zero voltage where it's most convenient for us. In a DC circuit, where it's convenient for us is often at the lowest point of energy in the circuit, so we don't have to deal with negative voltage. But know that negative voltage is a thing that is allowed in circuits, and it's in fact quite necessary to deal with alternating voltage circuits or AC circuits. Speaking of AC, let's talk about current. Current is defined as the flow of electrons through a circuit. We normally treat current as continuous value shared by the entire wire or component, even though electrons are discrete objects. Now we can make this assumption of continuity because of several properties of electrons. The first property is that electrons are very small. They have a mass of only about 9.1 times 10 to the minus 31 kilograms. In any given device or section of a circuit that we're likely to care about in this class, there are millions and millions of electrons. And this means that in effect, each electron contributes infinitesimally to the whole. So in practice, we can divide or remove any number of electrons without having to worry about it being an integer value. We can use it as a fraction. The other assumption is that current is the same across an entire wire or component, and we can justify that because of the natural tendency of electrons to spread out from each other. And this happens because each electron has a negative charge, and so they all have a negative charge, like repels like, and the electrons want to spread out from each other. And now that we're in a wire, we're in a finite space that they're trapped in, the electrons will spread out until they're equally distributed throughout the wire. And then given that equal distribution of electrons, when we apply voltage to that wire, they're all going to start moving at the same time, because that signal of when we turn the voltage on travels at the speed of light, because light is an electromagnetic wave, and so is electricity. So they all start moving at the same time, so there's no bunching as the circuit begins to move. In slightly more abstract terms, we can define current as a flux, where a flux is a rate of transfer through a surface. In our case, we are transferring electrons through a cross-sectional surface of a wire or component. And we measure this value in amperes, which have physical units of coulombs per second. Similar to voltage, we normalize this flux to a unit area. Because wires are going to have different gauges, they're going to be thicker, thinner, components will have different surface areas that they have to worry about. We're going to normalize this so we don't have to calculate a different current for every device or wire in our circuit. So the derived units, amperes, coulombs per second, has an implied unit area, but we don't usually include that here. Also, flux has both a magnitude and a direction, and this implies that negative flux is a possibility. And in fact, it comes up quite a bit when analyzing more complex circuits because we need to keep track of the directionality of current. More on that later on in the course. And then just like mechanics, circuits have non-conservative forces as well. The most basic of which is resistance, where resistance is defined as the resistance to a flow of electrons. This can come in the form of physically bumping into other particles or through opposing electromagnetic fields. Resistance is a property of the material that the electrons are moving through. And what this means is that no matter how many electrons we are trying to pass through, the resistance itself will remain the same for any circuit that we build in this class. There are some things that can affect the resistance of a material, such as temperature, humidity, some other stuff, but for the most part, we're going to assume that it's stable and consistent in our class. And if it helps you understand a little better, resistance is the same thing as friction. If we have a ramp as our corollary to voltage, where the high point and the low point are the high and low voltages of our circuit, and the block is our electron trying to move through, the force of friction slowing down that block is the resistance of an electron passing through a circuit. In more theoretical terms, we have our roots of resistance in solid state physics. And the material's resistivity is rooted in several factors, such as the material density, impurities in the material, and its composition. For many common materials found in circuitry, the density can depend quite heavily on the type of crystalline structure that the material exhibits. A few different examples of crystal structures are found on the right side of the screen. Skipping a lot of very interesting analysis, we can characterize the resistivity of a material as proportional to the charge density as well as the mean free time between collisions. For details on how we arrive at the equation, see Introduction to Solid-State Physics by Charles Cattell. So the mean free time, or tau, increases with less dense materials, which can cause a decrease in resistivity. And what the mean free time is the average time between collisions that an electron might experience. So if an electron is continuing in a straight line, how long on average until it runs into, let's say, a copper atom that it's traveling through a copper wire. If it's a very dense material, that time's not very long at all. So you're going to be losing a lot of that forward momentum by bouncing off of copper atoms. So you're going to have a harder time moving that electron through that material. And the opposite's also true. A very spread out crystal structure, that electron can travel in a straight line for a long time before it hits anything, so you lose less energy moving in through that material. And now the charge density refers to charges that are not moving in this case. So if you have like ions in there, like doped materials, which will come up when we talk about diodes later on, this can change the resistance of the material. And then the last slide is the practical considerations of resistance. So we have the resistivity of a material, which can be stacked on itself. So if it's a resistivity per unit volume, and we're moving through multiple unit volumes of the material, the effective resistance is higher than the resistivity alone, because you're moving through one unit of resistivity and another and another. So the total resistance of our component is proportional to the length of our path and the surface area normal to the path. Okay. And we measure it in units of ohms, or the capital omega, which have derived units of joules seconds per coulombs squared. And we're going to cover that and where that comes from a little bit more when we talk about Ohm's law in another lecture. But that's all for right now. Thank you very much.